Hello everyone, welcome back to the quiz tutorial. In this tutorial, we're going to be covering quiz number 11, which focuses on symmetric tensors. So again, if you hear tensor, don't worry about it too much. It basically, for you guys, just means a matrix. So tensor and matrix in this course are interchangeable. You don't have to worry about the different definitions and what they mean. Now, you guys are going to ask, what is a symmetric tensor? Well, symmetric tensor has a very unique property in a matrix that you guys will see that basically, for your guys' purposes, will just make calculations a lot easier. And that's great because no one wants to do crappy calculations. But although it makes the calculations easier, you guys are really going to have to know the properties of a symmetric tensor, because what's going to happen in the midterm is there could be a crazy, disgusting looking matrix or tensor. And if you guys don't know that it's symmetric and has specific properties, you guys might try and calculate things the long way or the hard way. And as you guys will see, it's a complete nightmare. But if you know the properties of a symmetric tensor, you guys can say, okay, well, there's a lot of simplifications we can do. And a lot of times, which you guys will also see in the quiz, we can jump to the answer really, really fast with very little calculating involved. So with that being said, let's jump into the theory to find out what exactly a symmetric tensor or symmetric matrix is. Alrighty, so I know the question you guys are all asking yourselves is this. Well, what is a symmetric tensor? Well, a symmetric tensor, by definition, is symmetric if S is equal to S transpose. In other words, the components Sij are equal to Sji. And this is better if I show an example. So let's say we have a typical matrix or tensor S with the following components. So it's very standard, S11, S22, S13, S21, etc., etc. Well, we say that this tensor is symmetric if S21 is equal to S12. So Sij is equal to Sji. So if we look here and we know that the tensor is symmetric, well, then those parameters in red, the S12, the S13, and the S23, we already know because it's symmetric. And this is why this is such an important concept. I know Dr. Sam really harped on this in class, that symmetric tensors are very important. Well, this is why. If we had the matrix on the left, or the tensor on the left, we have 9 parameters. So if we're trying to describe a material using an asymmetric tensor, we're going to need 9 different parameters to characterize that material. However, if we know that the tensor describing that material is symmetric, well, then that limits our parameters down to 6. So it's much easier to define that material. And as you guys will see with elastic materials, this is exactly what happens. So let's just go over a quick example. Let's say we have a matrix S and we're curious. We're going to say, okay, well, is this tensor symmetric? Well, the best way to do it, for me anyways, is I like to draw a nice horizontal line down, and then I compare the off diagonals is what I call them. But basically, if I were to look, I could say, okay, S12 is equal to S21, which is 4, and it's 4 on both sides, good to go. S13 is equal to S31, which is -3. And finally, S23 is equal to S32, which is equal to 2. And since all those components are equal to each other, I can conclude that yes, this tensor S is symmetric. So another very important property about these symmetric tensors is diagonalization. And I'm not sure if that's the official term for it, that's just what I call it, because I guarantee if you call it this, you'll never forget what exactly it is. So if S is an n by n symmetric matrix, or tensor, I'm going to keep going or tensor or matrix the whole time, I'm going to drive you guys nuts, but S has n real eigenvalues with n orthonormal eigenvectors. So if we were to look at this and say, okay, well, let's say we have a matrix S, which is the very typical standard matrix, and we have Q. Now, Q is going to be special because it is a coordinate transformation matrix, but the rows of Q are the eigenvectors of S. So if we know the eigenvectors P, Q, and R, well, then we can have a specific coordinate transformation matrix made up of those eigenvectors. And if we were to change the basis using this matrix Q, well, we go S prime is equal to QS times Q transpose, and what we'll end up with is a very special matrix, a diagonal matrix. So if we look at this matrix, all of the diagonals have a value, so S11, S22, S33, but the rest of the values are 0. And this matrix is very special because all of those diagonal components are the eigenvalues of S. So in this case, that first one, that lambda P, would be the eigenvalue corresponding to the eigenvector of P. And this is going to play a very important role in our calculations, because if we were to look at this and say, okay, this is a change of basis, well, that means that all of the invariants are also the same. So I1 of S prime is equal to I1 of S. And since we know that I1 of S is the trace, I1 of S prime is the trace, Well, we know that that's going to be equal to lambda p plus lambda q plus lambda r. And very similarly, for invariant number 3 of s prime, which is the determinant of s, we know that the determinant is going to be equal to lambda p times lambda q times lambda r. So it's very, very nice for us because in a lot of these questions, you guys will see is that we will give you guys the eigenvalues. So you guys will know lambda p, lambda q, and lambda r. And from that, you guys can calculate the determinant or even the trace of s prime. And since you know that s prime is just a change of basis of s, we can go one step further and say, okay, well, if we give you lambda p, lambda q, and lambda r, then you can very immediately determine the determinant or the trace of our original matrix S. So this is why I play such an important role, because it really simplifies our calculations and makes things very quick to determine. Now, if you forget about all these special properties, well, you're going to be doing things the long way. If it wants a determinant, then you're going to be doing a nice long calculation, something like that. But if you know these properties, it'll save you guys a lot of time. And that's exactly what you guys are going to see in the quiz that we're going to start right now. All right, guys, welcome to the quiz. So the quiz itself, 4 questions, well, 5 questions. 4 out of the 5 questions, they're pretty simple as long as you know the properties of a symmetric matrix. If you don't, well, they're not so simple. They're a big pain in the ass. But that last question, question 5, it has a little bit more work, but in the end, it's not too bad. Again, we're going to have to use all the properties of a symmetric matrix to really figure out these questions. So let's take a look at question number 1, which says, consider the following symmetric matrix. So we have a matrix S, which is 2, 0, 0, 0, 0, 1, and 0, 1, negative 2. And we know it's symmetric because the value of this right here, which should be S3, 2, is equal to S2, 3. And of course, the other ones too are also symmetric because 0 is equal to 0 and 0 is equal to 0. So we do have a symmetric matrix on our hands, so that means it has special properties. And that first one that I want to talk to you guys about is the last one that we covered in the slides, is because we know that there's a matrix, since this is symmetric, there's a matrix S prime, and I'm just trying to make this a little bit nicer. That's a diagonal matrix that has the diagonal values of the eigenvalues of matrix S. So we know that because this matrix is symmetric, there is a matrix S prime which has the following form. And this is kind of the key to solving this question. Because the question says, if the eigenvalues of S are lambda 1, lambda 2, and lambda 3, which we just put up there, which of the following statements is true? So we're going to start off with part number C, because part number C is just what we talked about. It says there is a coordinate system in which S has the following form, where S prime is equal to lambda 1, lambda 2, lambda 3 in a diagonal form. And we just discussed, yes, that's the kind of a special property of a symmetric matrix. So we know that C is definitely true right from the start. The second thing that we can do is we can look at part B, which says lambda 1, lambda 2, and lambda 3 are real numbers. And if we have a symmetric matrix, again, this is another property of a symmetric matrix, it will always have real eigenvalues, always. So from that alone, we can say, okay, yes, part B is also for sure correct. And since we have 2 correct, well, then we have to go to statement D, and we know it's going to be all of the above for sure. But let's just take a quick look at statement A, because statement A is a lot of fun. It says lambda 1 plus lambda 2 plus lambda 3 is equal to 0. And it's going to say, oh, that's kind of iffy. That's not one of the properties we're usually given all the time. So we're going to have to realize this, is the invariants of S and S prime are the same. So if we were to look at invariant 1 of S, we know that that's going to be the same as invariant 1 of S prime. Because remember, S prime is obtained just by a change of basis. And if we change the basis of something, then the invariants stay the same. And we know that the invariant 1 is the trace. So we know that the trace of S is equal to the trace of S prime. And this is just the sum of those diagonal components. So if I were to go with the trace of S right now, so TR of S, I'm just going to sum up all the diagonal components. So it's going to be all of those right there. So we know that this is going to be 2 plus 0 plus, and then we have a negative 2, which is equal to 0. And this is equal to the trace of S prime. So S prime, we're just taking all those diagonal components yet again. So it's going to be lambda 1 plus lambda 2 plus lambda 3. And if we look at this statement right here that we just kind of proved, well, that's the same as statement A. So we know that statement A, of course, is also true. So all 3 of those statements are absolutely true. Therefore, the answer to question 1 is D, all of the above. Now we can come down to question number 2, which again says, considering the following Symmetric. That should be a good term. Symmetric matrix. And it says if the eigenvalues of S are 0, 1, and 2, then the following is an eigenvector of S. So this question's kind of funny because it doesn't really utilize the properties of a symmetric matrix. It just wants you to figure out what an eigenvector of the matrix is. And the best way to do this is by just going to the definition of an eigenvector. So remember, for an eigenvector, which we'll call P, M of P is equal to lambda P. So all I'm going to do is I'm going to substitute these values in and just see if the statement holds true for all three. So for the first one, if I were to come down, I know that my matrix M, which I'm just going to kind of put like this, is 1, 0, 0, 1, 0, 0, and then 0, 1, 1. And I believe it's 0, 1, 1. I'll just double check. Yes, it is. So for this to hold true, what I'm going to do is I'm just going to take that first eigenvector that they give me, or at least we think it's an eigenvector. We're going to see if it's not. So here I'm going to take vector A, which is 0, 2, 2, 0, 2, 2. And I'm going to put this down like this. So if we multiply these two matrices together, which is basically, I'm just doing this part right here, this MP, I get the following matrix. 0, 4, 4. And I know I'm trying to make this look nicer for you guys with the nice square brackets. So I get this matrix 0, 4, 4. So that comes from just multiplying M and P together. And if it's an eigenvector, then that means that this is equal to lambda multiplied by, the original eigenvector. So this would be 0, 2, 2. 0, 2, 2. And if I look at this, then go, well, yes, it's pretty easy to see that in this case, lambda must be 2. And that makes sense because if we look above, it even says that there is an eigenvalue of 2. Because if we multiply the matrix here by 2, or sorry, if we say that lambda here is equal to 2, well, then those vectors are the exact same. So we know that A is definitely an eigenvector. So we're going to circle it. But now if you guys are wondering, what happens if we pick an incorrect answer? So let's pick answer B. So if I were to do the same thing and multiply the same two matrices together, not the same two, if I go M by the new matrix, which I'm not going to show because it takes too much time, what you end up getting is 0, 3, 3. So this right here is I'm just going to put, I probably should put a little bit more context. This will be matrix M, which I don't want to write out again, multiplied by the vector from part B. So I'm just going to put my nice square brackets here. I hate drawing square brackets. This is the worst part about linear algebra is all of this stuff. So this would be by 0, 1, 2. So this is the answer for part B, or I guess the statement part B. And this is supposed to be equal to lambda times what we had in B. So we know that B was 0, 1, 2. And as you guys can see here, there is no possible way that any lambda will give us this, because in order to go from, and I'll do this in a different color, let's say to go from 1 to 3, lambda has to be 3. But if we go from 2 and we times that one by 3, we get 6. We don't get 3. There's no possible lambda to actually map these together. So therefore, we know that B is for sure not an eigenvector. So you guys can do this for vectors C and D if you guys really want, feeling brave, but you don't need to. We found the correct eigenvalue already, or sorry, eigenvector already, which is A. So we're going to move on, and this question right here, this question 3 is a great example of why we need to know the properties of a symmetric matrix. So it says, consider the matrix S, and S is just disgusting. But we can tell that it definitely is symmetric because S12 is equal to S21, and so on, and so on, and so on, and so on. So we know that it's symmetric because all those values line up. So the question says, if the eigenvalues of S are equal to 2, 3, and 1, then the third invariant of S is equal to, and it gives us 3 different answers. So this is when we're going to have to use the properties of symmetric matrix. So remember that there exists a matrix S prime, and we say that since it's through a change of basis, invariant 3 of S is equal to the invariant 3 of S prime. And we know that the invariant 3 is just the determinant. So this is going to be the determinant of S prime. So if you guys remember what S prime looks like, it's a diagonal matrix right here. And it's very, very simple to prove. But we basically have lambda 1, lambda 2, lambda 3, and the rest are zeros. finish them all up here. And if I come down, you guys will see that if I were to take the determinant of this, the determinant of s prime, so I guess I'll put s prime is equal to, determinant of s prime, which is the answer we want, is equal to lambda 1, lambda 2 times lambda 3. So the answer to this question right here is we just multiply all three of those determinants that we were given. So it says that the eigenvalues that were given. So the eigenvalues are equal to 2, 3, and 1. So all we have to do is say the invariant 3 is equal to the determinant of s prime, which is going to be 3 multiplied by 2 multiplied by 1, which gives us 6. So we can circle 6 and say, yes, this is our answer. But if we were to look up at this matrix and let's say you forget about the properties of a symmetric matrix, then this question is going to be a nightmare. Because look at all those decimal places. Oh, it's just going to be disgusting. But now that we know it's a symmetric matrix, we can say, okay, well, the determinant of a symmetric matrix is equal to the 3 eigenvalues multiplied together. And we were given those 3 eigenvalues, which was very nice. So we can conclude that the answer is indeed 6. So moving on, this is our last kind of nicer question before we get into a longer question, which is question 5. And it says, let Q, S, and S prime be three-dimensional matrices. Assume S to be a symmetric matrix and Q to be an orthogonal matrix. And that's important because if that's the case, then what we do is we can do S prime, which is equal to QS, QT, and I don't know why that didn't straighten. Hold on. So we can do this right here, which is a change of basis. And this is really going to test our knowledge on the properties of a symmetric matrix. Because if you guys remember, if we have S prime in the following form, that diagonal form, then we know that those 3 values right there are going to be the eigenvalues. So if we come down here, the first question, lo and behold, says, what are the eigenvalues of S? And if we go, okay, well, we know that it's going to be 8, it's going to be 4, and it's going to be 3. So there's a vector here, B, which is 8, 3, and 4, so that must be it. And you guys know that one. I'm pretty sure that you guys are going to be fine with finding eigenvalues. And then it says, well, the eigenvectors of S is this. And it gives us 3 different options. And then the special option, none of the above. So if you guys are feeling brave, just go for none of the above. That's what I would usually do in an exam. And it doesn't usually work out. So what we have to remember for a symmetric matrix is, because I know you guys are so good at the diagonal matrix, is we have to realize that there's a special quantity Q here. And if S prime is equal to QS QT, and that's equal to a diagonal matrix, then what this means is that the rows of Q are the eigenvectors. So these 3 right here, these are the eigenvectors of S. So our first one is root 3 over 2, negative 1/2, and 0. I come down here and I say, okay, well, that doesn't appear anywhere. Oh, the second one, I get 1/2, root 3 over 2, and 0. I come down, okay. Oh, that one also doesn't appear, so maybe it will be none of the above. But then if we look at that last column, or sorry, that last row right here, we see that one of the eigenvectors is 0, 0, 1. And if I come down here, oh wait, 0, 0, 1 is answer B. So therefore, yes, there is an answer there. So if you guys took my strategy of none of the above, you guys would regret it immediately. So we have an answer B, and that's because remember that the rows of Q are the eigenvalues of S. If S prime is equal to QS QT, and that's a diagonal matrix. So again, easy questions. They look pretty difficult, but once you guys remember the properties of a symmetric matrix, it's pretty easy to go through. Now, question 5. It does use the properties of a symmetric matrix a little bit in part C, but part A and B, it's just straight up calculations, which always sucks, but you guys need to know how to do it, so let's do it. So considering the symmetric matrix, and it's nice because it's 2 by 2, and it says determine the eigenvalues of S and the eigenvectors of S. So those are the first 2 I'm going to do. So I'm going to come down here and say, okay, well, part A, eigenvalues. I know that to find the eigenvalues, I need to take the determinant of S minus lambda I is equal to 0. So, all right, so the determinants, well, that can be expressed kind of as these absolute value signs. So S minus lambda I, well, that's going to be negative 0.2 minus lambda, and then the second entry stays the same, so this will just still be 2.4. Or is it negative 2.4? Negative 2.4. And same on this side. Again, it's symmetric, so that should be. And then we have 1.2 minus lambda. So 1.2 minus lambda. And remember that this determinant here must be equal to 0. So in order to solve for lambda, we can expand it out. So what we're going to do is we're going to come down here and say, okay, well, we have negative 0.2 minus lambda multiplied by 1.2 minus lambda. And then this is subtracted from negative 2.4 and negative 2.4. And of course, this is all equal to 0. So if we look here, well, we have lambda, we have another lambda, we can kind of see that, all right, this is going to be a quadratic equation. So let's simplify it a bit. So if we do all the simplification, what we get is we get lambda squared minus lambda, and then minus 6 is equal to 0. So this is our quadratic equation. We can go and use the quadratic formula if we want, but this one's pretty easy to tell that, okay, well, the roots of this are going to be lambda minus 3, or I guess this can be factored into lambda minus 3 and then lambda plus 2, and this is equal to 0. So from here, we know that lambda must be equal to either 3 or negative 2. So these right here, which I'll circle in a different color, these are going to be my eigenvalues right here. So the first part, finding eigenvalues, is usually not too bad. Eigenvectors is the thing that kind of sucks a little bit more. So part B wants us to find the eigenvectors of those eigenvalues. So what I'm going to do is I'm going to go part B, and then we have to remember, okay, well, an eigenvector P has the form MP is equal to lambda P. And we now know what lambda is. We know what M is. Our only unknown in this equation is going to be the vector P. So what I can do for the first lambda is I come down and say, okay, I'm going to have my M matrix, which is negative 0.2, negative 2.4, negative 2.4, and 1.2. So again, we already know M. When you're given these type of questions, you will know the matrix M. It'd be kind of hard to give you an eigenvector and then tell you to solve for M. But we come down here and say, okay, well, our eigenvector is going to have the form P1 and P2. I'm going to finish this off. Well, you guys are going to be real sick of me drawing these square brackets by the end of the day. This is going to be equal to lambda, and we have two values of lambda. So what I'm going to do is I'm just going to keep it as lambda for now, and you guys can switch it around if you want. So lambda here, and then what I'm going to have is I'm going to have P1 and P2. So just like that. All right. So from here, what we can do is we can basically create two equations. And in the end, they're going to have two unknowns. So the first equation, it'd be negative 0.2 times P1 minus 2.4 times P2 is equal to lambda P1. And my second equation is going to be negative 2.4 P1 plus 1.2 P2, and this is equal to lambda P2. So if we try and solve this really quick, let's say that we throw lambda is equal to 3 in here and solve, what you guys will find is that this right here has infinite solutions. So I'm going to try and draw the infinity sign. Oh, that looks terrible. Kind of looks like a pair of glasses. So infinite solutions. So therefore, what we need to do in this case is we're going to say, okay, well, let's say that P1 is equal to 1, and not P1, sorry. I always do the bottom one. So this will be P2 is equal to 1. Well, in this case, I can go up to equation 1. So let's say that we are solving the case of lambda is equal to 3, and we go up to equation 1. So what I'm going to do is I'm going to put equation 1 down here. I'm going to say negative 0.2 times P1 minus 2.4, and we know that P2 we assumed is 1 is equal to lambda P1. And we're saying if lambda is 3, this will be 3 P1. So from here, what we can do is we can say, okay, well, we can solve this very easily and find out that P1 is going to be equal to 0.75, just like that. But now we're going to say, okay, well, we got P1. We already said P2 is 1. So technically, our eigenvector is going to be this. It's going to be P is equal to 0.75 and 1. Now the problem with this is that it's not normalized. And recall that since there are infinite amount of eigenvectors, we usually organize them. Yeah, we do organize them, but we normalize them so that they have a unit length. So to do that, all we have to do is normalize them. What you guys will find is this vector is the same as this is negative 0.75. Should have made that clear, and you guys will see in your calculations that it's negative 0.75. So if we normalize the negative 0.75 and 1, we get negative 0.6, and we get 0.8 at the bottom. So this is the eigenvector for lambda is equal to 3, because remember, we have to solve this equation twice. So if I come back up to the top here and say, okay, well, now I got to solve the other one. So I'm going to take equation 1, I'm going to come all the way down here, and I'm going to solve it for lambda is equal to negative 2. Well, I'm going to get the same equation on the left-hand side, where I get 0.2 p1 minus 2.4 times 1. But now this is equal to negative 2 times p1. And what we can do is we can say, okay, well, my only unknown here is p1. I can have p1 is equal to 4 over 3. Or 1.33333 dot dot dot. I just don't like writing it, so I'm going to go 4 over 3. And in this case, my second eigenvector, p, is going to be equal to, I'm trying to keep this nice, I know it's starting to look more and more messy as I go, it's going to be 4 over 3 and 1. So this is why we can assume that that one, oops, that looked really bad. We can assume that that P2 is equal to whatever we want, because once we normalize it, we'll always get the same form. So I come down again, another square bracket, and if I normalize this, what I get is I get 0.8 and 0.6, just like that. So those are the, oh, they added curves now, I see, interesting. All right, I'm so sick of these brackets. Finally, we're done. So I know it's a little bit of work to find eigenvalues and eigenvectors. They really suck a lot. So, I should probably also just put, this is for lambda is equal to negative 2. All right. So back to where we were. So this is how you find the eigenvalues and eigenvectors. Eigenvalue, not too bad. Eigenvalue, well, it's a bit more work. And I should probably take my glasses. I should probably turn that back into an infinity sign instead of glasses. All right. So the final part of the question says, find the components of S prime in the coordinate system formed by the eigenvectors of S. So there's two ways to approach this problem. One is, you know, just from before, that S prime is equal to QS QT. And then since Q is going to be a function of the eigenvectors, what you guys can do is say, okay, well, Q is going to be eigenvector 1 and then eigenvector 2. So if you wanted to, in this case, you can say, well, eigenvector 2 is 0.8, 0.6, and this one's 0.6 or negative 0.6, 0.8. You can do that, and you can do all the calculations, have a lot of fun. No, it's because I'm trying to do half the square bracket. All right. Nope, doesn't want to work with me. All right, let's try one more time, and then I'm going to give up. All right, I give up. It's just going to be like that. So we can say, I'll put right here, this is eigenvector 1, eigenvector 2, basically, for the rows. And we can do that. But we also know that S prime, if it's formed by the eigenvectors of S, well, we know that that's just going to be a diagonal matrix. So we already know that S prime is going to be, and I thought I was done with the square brackets, but there's always a little bit more, hey? So we know that this is going to be lambda 1, lambda 2, and then the rest are zeros. And we already know what lambda 1 and lambda 2 are. So that curve, ooh, it's bad. All right. So we know what lambda 1 and lambda 2 are. So once we actually found the eigenvalues in this question, we could have done part C. We didn't need to know the eigenvectors. So we know that this is going to be 3, that's 0, this is 0, and this one's going to be negative 2. So if you guys wanted to, you guys could have went through and did all the calculations. But if you remember those properties of a symmetric matrix, you guys could have just jumped to the end right there. And that's it. That's question number 5. I know it took absolutely forever. My voice is going to give out right before the seminar here, so hopefully I'm not coughing too much in the seminar. But yeah, I hope you guys learned something. Again, symmetric matrices are going to be very important for you guys moving forward. I know that I probably didn't do the best job of question 5. I just got so sick and tired of drawing those brackets, but I hope you guys understand. So thank you guys so much for listening. Thank you for all your support on the videos. It means a lot to me that they're actually helping you guys. Again, if they help you guys, then I'll create many, many more, as long as they're helping you guys. If I'm creating more questions than answers, well, maybe I should stop. So, so far so good, but we'll have to see how it goes in the future. So thank you guys again so much for listening. I will see you guys in quiz number 12.